In this video, we are going to learn about the operational amplifier. We'll discuss how the operational amplifier works and its most common applications. An operational amplifier, or an op-amp for short, is basically a signal amplifier. It's not just a signal amplifier though. You can design to perform mathematical operations as well, which is why they're called operational amplifiers. We'll learn about that in our video lessons. At this point, you can now imagine how transistors are really the most basic of all electrical components, in that we can practically build these operational amplifiers from the transistors in order to perform mathematical operations. The schematic symbol for the operational amplifier is shown in the figure. You generally have two inputs, the inverting and non-inverting input, and one output terminal. The operational amplifiers require two DC voltages as shown in Figure B. Oftentimes, when designing circuits, the DC sources are not included for simplicity. The typical packaging for the op-amps are also shown. These packages depend on the specific applications or how these op-amps will be mounted on a circuit board. In our last video lesson, we've discussed the differential amplifier and have shown how they operate. You can in fact think of the operational amplifier as having these two exact same inputs as the differential amplifier, and then get the output from any of the two outputs, since the outputs are exactly the same with the only difference being that they are 180 degrees out of phase relative to each other. Let's now consider the characteristics of the operational amplifier, beginning with its ideal characteristics. The ideal op-amp has an infinite voltage gain and an infinite input resistance. The input resistance is sometimes called the input impedance. It also has zero output impedance. The input voltage is the voltage across the two input terminals, and the voltage gain is multiplied by the input voltage to get the output voltage. In practice, op-amps have high voltage gain, high input resistance, and low output resistance. We'll now describe the process of amplification. To do that, we define what a negative feedback is. Negative feedback is the basic process of returning part of the output signal to one of the input terminals, specifically the inverting input, with the phase angle that opposes or subtracts from the input signal. Its basic configuration is depicted in the figure. Remember that any difference in the signals between the inverting and non-inverting inputs are amplified. By sampling the output signal back to the inverting input, the non-inverting and inverting inputs become nearly identical. Remember that the basic amplifier is a differential amplifier, and whenever the inputs of the differential amplifier are the same, the differential amplifier cancels the signals and gives zero output. The feedback network controls the amount of gain that the op-amp will deliver. To guide you in analyzing op-amp circuit applications, remember these two golden rules. The first rule states that the input draws no current. This is a consequence of the infinite input impedance of the ideal op-amp. Because of the infinite impedance, no current could be seen between the two inputs. The second rule states that the output will do whatever it can to make the voltage difference between the two inputs zero. This forms the basis of how to design the feedback network. We'll now apply these rules to our negative feedback op-amp circuits in the next slides. The simplest type of op-amp circuit is the voltage follower. The feedback is just a straight connection between the output and the inverting input. According to golden rule number 2, the inverting and non-inverting inputs should be equal. Thus, the output voltage is equal to the input voltage and the voltage gain is unity. What about its input and output resistances? The practical input and output resistances of the op-amp can be found in the datasheets for each type of operational amplifier. These resistances are measured without any input or output signals present and without any feedback. The expressions for the input and output impedances with feedback are given in terms of the input and output resistances and the open loop voltage gain, A sub OL. The open loop voltage gain is the intrinsic gain of the op-amp without any feedback. It's also indicated in the datasheets. Typical values are in the hundreds of thousands. Let's apply the golden rules to the non-inverting amplifier. We label the non-inverting input as V+, while the inverting input as V-. The non-inverting input is just equal to the input voltage. The inverting input is the output taken at R sub I with respect to ground. We recognize the feedback network to be the voltage divider. Thus, the inverting input is then an equal to the output of the voltage divider when the input of the voltage divider is the output of the op-amp. According to golden rule number 2, the output will do whatever it can to make the inputs equal to each other. Since the voltage gain is defined as the output voltage to the input voltage, then the voltage gain is given by the equation shown. This type of amplifier circuit is called the non-inverting amplifier. You can control the gain based on the values of the resistors used in the feedback network. The input and output impedances are given by the equations shown. The variable B is called the attenuation, and in this case it's just the inverse of the voltage gain. Thus, you can see that the input impedance with feedback becomes higher than the input impedance without feedback, becoming nearer to the ideal case, and that the output impedance with feedback becomes lower than the output impedance without feedback, also becoming nearer to the ideal case. In this circuit, the non-inverting input is connected to ground. This means that according to golden rule number 2, the inverting input is also grounded. According to golden rule number 1, no current is being drawn through the inputs. Thus, the current flows from the input voltage through R sub I and then through R sub F towards the output. The input current is therefore the same as the feedback current. We can solve for the input current with respect to ground to be equal to the input voltage divided by the input resistance. We can also solve for the feedback current with respect to ground to be equal to the negative of the output voltage divided by the output resistance. The sign is negative since the current flows from the ground to the output terminal. Since the input current and the feedback currents are the same, then solving for the voltage gain, we have the expression shown. This circuit is called the inverting amplifier. For the inverting amplifier circuit, the input impedance is just the same as the input resistance, while the output impedance has the same expression as with the non-inverting amplifier circuit. I hope you've understood the lessons in this video. We've discussed what an operational amplifier is and its basic characteristics, including the negative feedback. We've also discussed the golden rule of operational amplifiers and applied these rules to 3 simple op-amp circuits. In the next video, we'll discuss more op-amp circuits. This will be followed by a third video discussing examples on how to solve problems involving op-amp circuits.